All right, we just want to do a review of reactions from statics. I think this is on 760 of your book, if I remember right. All right, so this is just a review of things that we've done in statics. We're going to start getting into beam design, and we use reactions. It's a step that we use to take so that we can go ahead and figure out what's going on inside of a beam as far as the internal shear and moment. So this is the first step in doing that. And we just want to go over this a little bit just to be sure that you remember this stuff and that you can do it when you need. So this is on page 760. All right, so the basic deal here with reactions is you have supports and you have applied loads. So in this case, we've got 2,000 newtons there that's applied 6 meters on what we would call a simply supported beam there. And what we want to do then is to figure out what the reactive forces are at the supports. How do those supports react when you push down with 2,000 newtons? All right, now we got 3 equations we can use, and we're doing 2-dimensional statics. We got this force equation, sum of Fx is 0, sum of Fy is 0. And then we can take moments about any point we want and set that equal to 0. So step 1 is to draw a free body diagram. So we've got the 2,000 newtons right there. And then we have these unknown forces at the support. So we've got an upward force at A and another one at C. Now that's a pin joint there, and what it does is it constrains motion up and down, and it also constrains motion left-right. So we'll have RAX and RCX also, or at least the potential for those. Now I'll notice that there's no applied forces in the X direction, so both RAX and RCX will be 0. All right, so that leaves me with RAY and RCY. Now, I'm not doing anything in the X direction, so that equation I'm not going to use. So that gets me 2 equations. I've got 2 unknowns, so I can solve it. Now, if I start with sum of Fy equals 0, I'm going to involve both of the unknowns, RAY and RCY. So what I'm going to want to do here is start with a moment equation and set that equal to 0. All right, now if you just stop and maybe pause the recording and think for a second where you take moments about and then start to solve that, it might be a good thing to do. All right, to kind of think this stuff through on your own, which I think is a more effective way to learn than just to listen to me. All right, so if you give that a bit of thought, what we're going to want to do on this is sum moments about either A or C. And the reason for that is if we sum moments about A, we'll eliminate RAY from the equation because it'll have a 0 moment arm. The only thing that will be involved then is RCY. So if I take sum of moments about A, I can solve for RC. All right, so I'll have 2,000 times 6 meter moment arm. The 6 meter moment arm is perpendicular to the 2,000 Newton force, and that'll come around clockwise, so it gets a minus, okay? So minus 2,000 times 6, and what reacts again to that is RC with a moment arm of 6 and 2 makes 8. So that'll be positive. We can solve for RC, it's 1,500 newtons, okay, up. Now I've used that moment equation. Now I can use the force equation because I've only got one y unknown, it's RA. So sum of Fy is 0, RA up minus the 2,000 plus the 1,500, so RA is 500 newtons. Okay, so those are the 2 reactions. So 500 at A, 1,500 at C. All right. Now the next one here, what we've got is we've got a distributed load from A to B, 5 kilonewtons per meter. And then we've also got another point load there at C, and we got the dimensions down below. So again, it's a simply supported beam, no applied X forces, so we got RA and RD. Now what we have there on this one is a distributed load, so what we want to do is to find the area under the load diagram, and that'll tell us the force. So notice that's 4 kilonewtons per meter. Think of that as being the height of that rectangular load. It's over a 4-meter span, so between those two, you should be able to come up with a load in between A and B. That load then is applied at the centroid of the figure. That's a rectangle, so the centroid is right in the middle at L over 2, L being the base. Okay, so why don't you pause and work through that, see what you come up with for the reactions, and then we'll have a look. All right, so here are the reactions. So we got the 20 kilonewtons, so 20,000 newtons there is the downward load, 5 kilonewtons times 4 meters. It's negative because it's down. Now that's located at the midpoint of that 4-meter long rectangle, so that's half of that. That's at 2 meters. That's where that load is. It's right here. So the moment arm on that will be half of 4. It's 2. That's going to come around clockwise, so that's negative. Then I've got this 4 also that's coming around clockwise too, so that's negative 4 kilonewtons times a 6-meter moment arm. 4 and 2 makes 6. Then I have 8 times RD that pushes back. So I can solve for RD, it's 8 kilonewtons. And then once I've got RD, I can just do sum of Fy to get RA. Got RA up, 20,000 down, 4,000 down, 8 back up, 16 kilonewtons up for RA. Okay, so that gets me RA and RD. Notice that the load is closer to RA, so the reaction RA is larger than RD. Okay, the next one there is a couple. All right, now that's just a pure twist with no associated moment arm. Okay, if you remember this from statics, common way to model a couple is to think of having what I call a T-bar wrench on that, maybe like what you'd use as a lug wrench, or perhaps the wrench that you open and close the water valve outside your home with. Just trying to think, you know, those are common applications for this. And one way to model this is to have an upward force and a downward force that are equal in magnitude, and they're offset by a certain distance. Okay. Now, being as these forces are equal in magnitude, there's no associated force with that twist. It's just what I call a pure moment, a pure twist. If you think of a doorknob and how you turn a round doorknob, you just grab it and grip it with your hand and twist it. You're not pushing the doorknob left, right, or up or down. You're just twisting it. That's what a couple is. So a couple has a couple things about it that might be a bit peculiar. First is there's no associated forces. They cancel out. And the other thing is that there's no moment arm when you run the equation with them, because the moment arm is already in there. It's Newton meters. That's already a moment. It's already got the moment arm embedded in it. All right, so probably I'd start off by taking a moment about A and seeing what I could do to solve RC. So maybe again, just pause for a minute and see if you can work out RA and RC. All right, here we go. So we're going to have 3,000 clockwise again, so it's negative. Plus 3 and 2 makes 5 times RC. So 5 RC is 3,000, RC is 600 newtons up. Then I can go sum of Fy equals 0, and I'm going to have RA, which I assumed up, plus 600 is 0, so RA is actually negative 600. So what I've got there is I'm twisting this beam. I'll think of it as like a bar. I'm pushing it down hard at C, so C reacts upward. And I'm pulling it up from A, so A pulls it back down to prevent it from moving. Okay, so that's what's going on with that one. Okay, the next one here is a triangular load on a cantilever support. Now a cantilever has this beam either embedded in the wall like that, or it might have L brackets on there that are used to bolt that beam securely into the wall. So you might have bolts there, and then of course you'd have bolts that bolt into the beam. So that prevents any twisting at the reaction at A. So as a result, you get a reactive moment, which is a couple. So I call that MRA, the reactive moment at A. Okay. All right, and then you've got the upward reaction at A. So we'll call that RA. And then we also have a possibility for RAX. But when I notice that there's no X applied forces, I know that that'll just be 0. So I'll just deal with RA there, okay? And I'll call it RAY, I guess, just to be consistent here. Now I've got a distributed load, a triangular one, so I'm going to get a downward force associated with that. That force equals the area of the triangular load there. And then I'm going to apply that at the centroid. Now the centroid of a right triangle is located 1/3 of the distance from the right angle. So that downward force there, what we'll start by locating it from B. Okay, so the centroid of a right triangle, which is where you'll apply that load, is a third of the way over. So there's a third right there. You're left with 2/3 on this side. So why don't you go through that and solve for MRA and RAY. Pause before you do it, and then we'll have a look. Okay. All right, so here we go. So we've got 1,800 newtons per meter at the far end, times the base of 4.5 meters, and times 1/2 because it's a triangle. So that gets me 4,050 downward, 5 meters from A. Now to get the 5 meters there, what I'm doing is I'm taking 2 plus this distance here. Now what that distance is 2/3, because I'm coming from the vertex, not the right angle. And then I multiply that by 4.5. Okay, and that'll get me 3. So that's how far over from that vertex at B the centroid is. That's where I apply the load. So if that's B over 3, this is 2 times 2/3 of B. Okay, that's what I'm doing there. All right, so 2 and 3 makes 5. So the moment about A is whatever that reactive moment is, minus the 4,050 times 5 meters. So I can solve for the reactive moment. It's 20,250 Newton meters. I can go sum of it. Fx is 0, which is Rax, so that zeroes out. Sum of Fy is whatever Ray is, minus the 4,050, so Ray is 4,050. Okay. All right, the last one here, I've got a trapezoid, and the centroid for that is fairly difficult to find. So what I'm going to do is break it up into a triangle and a rectangle, each of which will have its own area and its own centroid. So I'll find the area of the triangle and apply that at the centroid of the triangle. And then I'll find the area of the rectangle and apply that down at the rectangle and combine those effects together. So the rectangle is the height that you see on the right, 3,000 newtons per meter. So that's the height of the rectangle. And then if you take what you've got total at the left, which is 7,200, and take away the 3,000 from it, what you get is the height of the triangle. So we got 7,200, we take away 3,000, and what we end up with then is 4,000. Or excuse me, 4,200, 4,200. So the height of the triangle is 4,200. Height of the rectangle is 3,000. So that's what we got, okay? So I've got a rectangle with a height of 3,000, triangle with a height of 4,200. They both have bases of 3. So I can go ahead and work through that. I want to find these two forces and their moment arms. So what I've got there, I've got a typo here. This is actually 1 meter here, and this is 1.5. Okay. There we go. All right. So I've got minus 4,200 times 3. That's minus 1/2, 4,200 times 3. That's the area of the triangle. 6,300, that's a meter from A, which is a third of 3. Because as we were discussed earlier there, the centroid of a right triangle is at the third of the base over from the right angle. And then the rectangular load is 3,000 times 3, 1.5, which is half of 3 from A, that's 3/2, okay? So now I've got those two loads and their moment arms. I can go ahead and run the moment equation and solve for the reaction at C. You can go ahead and do that, maybe pause and then check back in. All right, so negative 6,300 for the triangle times its moment arm of 1, minus 9,000, the load of the rectangle, times its moment arm of 1.5, plus 3 and 3 makes 6 RC. RC comes out to be 3,300. Sum of Fy is 0. RA up, 6,300 down, 9,000 down, plus 3,300 up. That leaves 12,000 at RA. So that's just a little run through reactions there, just for review. We'll get into shear and moment next time.